Okay, so, well, good morning, everyone. I'd like to welcome you and also thank you for joining us in this intensive lecture series by Quantum Gravity Gatherings. So this is the 8th time now, and this time it's our pleasure to have Professor Philipp Höhn from Okinawa Institute of Science and Technology, or OIST, to come and give lectures on quantum reference frames. And he's one of the leading experts in the field, so I hope we can learn a lot from him. So, yes. And okay, so without further ado, I will say the floor is here.
Yeah, thank you very much. And thanks also to Katarek and Höhn for the invitation. It's a great pleasure to be here. So indeed, I will be teaching you about some basics of quantum reference frames. So what are quantum reference frames? At a very basic level, they are the idea of associating reference frames with quantum systems. So in some sense realizing the idea that every reference frame in practice in physics is associated with a physical system, and then assuming the universality of quantum theory, that they will also be ultimately subjected to quantum theory fluctuations. And so in the beginning today, I will try to be, first of all, introducing some conceptual ideas underlying this whole program, because that is a bit different from what you may be used to with the standard notion of reference frames in physics, where you consider them as being external. And then later in the day, I will go into the more formalism. And really, one thing is, this is, of course, a somewhat informal lecture series, so if you have any questions, so I'm always going to abbreviate kind of reference frames just as QRFs. It takes a while to write this down. And really, to understand part of the motivation for this, what we're going to be after is a notion of relativity with respect to quantum reference frames, so that we have different different choices of quantum reference frame, and then of course the standard thing is when we have different reference frames is how do you change perspective. And so that ultimately comes down to the question of having a notion of relativity with respect to this. And to put this into maybe some kind of historical development, let's really take a step back and realize that we had different notions of relativities. And of course the first one really is Galilean relativity. So relativities usually come with I'm going to be a little bit colloquial here, with a relativity principle that basically says that all the laws of X, and X is some physical theory that depends on what kind of relativity we're looking at, are the same in every Y, and Y stands for some notion of reference frame. And in Galilean relativity, we have that X is basically mechanics, and Y is inertial frames. And then, of course, the standard thing is that this leads to a decomposition of space in different ways relative to different choice of inertial frames. So, we have some X, Y, Z maybe relative to one frame, and well, maybe something that's Z prime, Y prime, X prime. So the main thing is that different inertial frames decompose space in different ways. Really, when I say that, I mean it in orthogonal directions. And then, we can switch on the speed of light as being or really 1 over the speed of light, that this is non-zero. So at a finite velocity, so we're introducing a scale. And then we're going to special relativity, of course. And in this case, it's really, it's all the laws of physics minus gravity. and y is again inertial frames. And then obviously, as you know, now it's not only that different inertial observers will decompose space in different ways in orthogonal directions, but also space-time. So we have the relativity of simultaneity. And so it's different inertial frames compose space-time in different ways, space and time. All right, and then the next step was essentially introducing G also. So we consider the Newtonian constant now as being non-zero, and then you go to general relativity, and then we have X is supposed to be all the laws of physics, and Y is in every frame, so it's not only inertial anymore. And then we have, of course, that this decomposition of space-time in different ways to space and time really just becomes local now. So so far so good. This was basically the standard story, and as you can now maybe guess, when we go to quantum reference frames or a quantum notion of relativity, we also want to switch on H bar. And so we can tentatively call this quantum. And well, let me just write for the moment X equals question mark, because the question still depends a little bit on the circumstances. So it's the laws, which laws of physics should be invariant under changes of quantum reference frame, and then also ask why maybe something like a quantum reference frame. And then another question is, what do different pure Fs decompose it in different ways? So I'm not going to give you the answer here yet, because that hopefully will be answered later today. But the crux is really there's some kind of relativity principle in all these notions of relativity, and different frames always decompose a certain structure in different ways. And in the standard settings, it's these are notions of space-time. Now, when you think about this here, so the reason I also put question marks here is that just switching H bar on, of course, has no unambiguous interpretation a priori. It's a bit like with the Bronstein cube that you sometimes see in discussions of quantum gravity, switching certain coupling constants on. Because strictly speaking, you could of course say, having both C and H bar switched on, that's what standard quantum field theory is in Minkowski space, right? So, and we have a well-defined notion of relativity there. It's just standard special relativity. There's nothing else than that. And so clearly, when I put question marks here, I have to mean something else, because otherwise there's nothing new to do. And here's the conceptual leap. We're going to be internalizing reference frames. So what I mean by that is, of course, if you do quantum field theory in Minkowski space, you have your background Lorentz frames, and the whole purpose and life of these Lorentz frames is to define a a description of your quantum field theory. But of course, the Lorentz frame itself is not part of the quantum field theory that you're actually describing. And well, you can implement Lorentz transformations unitarily and so on. But really what we want to do is we take a step back and we include the reference frames in the description or in a composite physical system that we want to describe. And then basically what we want to do is reference frames are now going to be different subsystems of a composite system that we may be interested in. And we want to describe this composite quantum system from the inside. So of course, the composite system has to be of such a nature that it contains such kinds of things, and we'll see plenty of examples. So, and then really, quantum relativity is loosely speaking describing subsystems relative to one another. And you have, you can think about it as reference frames, and also in relative superposition. And we want to do relativity with that. Of course, I should add that, in fact, you can do internal reference frames also in classical theories. So you don't have, it's not strictly speaking something specific to quantum theory. But if you want to do quantum reference frames, that's the thing you have to do. In fact, the classical picture on this is probably something that we're going to be discussing in gauge theories and gravity at some point. Okay. So yeah, that's the basic idea. Yeah, the question is really, let me maybe write this. Core question is, how do you jump into a QRF perspective and how do you change it? So that's in some sense the core question of quantum reference frame relativity or quantum reference frame covariance. Okay. So you can of course ask, why should I do something like this? That is of course a legitimate question. Say a few words about that. So why quantum reference frames? So ultimately at a conceptual level, one main point is, in practice, all reference frames are associated with physical systems, you know, be it the walls of your lab or whatever, or the Earth or cosmological observations, and then, you know, invoking somehow the universality of quantum theory. There should be quantum reference frames. So this is, of course, maybe at some level also philosophical question, but can we have a description of nature where reference frames are included in the quantum theory itself, so from the inside? Then it turns out that, and this is a point that I will hopefully make clear tomorrow and maybe on Friday, they are always invoked when building gauge-invariant observables. Let me say physical observables in gauge theories. And gravity, really, also. So what I mean by that is in gauge theories and gravity, you have basically two means of constructing gauge-invariant objects. You can either, or physical objects, you can either gauge fix or you can dress observables. And essentially, it's the degrees of freedom that you're using to dress other degrees of freedom to turn them into something gauge invariant. Those degrees of freedom constitute your quantum reference frame for the gauge group. And similarly, the degrees of freedom that you fix when you gauge fix, those are the reference frame degrees of freedom. Yeah. So this, I'm just telling you that right now. This will become clearer hopefully tomorrow and afterwards. So in that sense, whenever you deal with gauge systems, you're actually implicitly using quantum reference frames. So in that sense, you can really view this as in some sense, a new paradigm of thinking about gauge invariance in such theories. So of course, in quantum gravity, we have absence of external background structures in general. Specifically, when we deal with closed universes, was in AES-CFT or so, where you have a boundary, you can always, in some sense, use the boundary as a reference for the bulk. But again, turns out that if you dress to the boundary, that actually turns out to also go to reference frames. But when you have closed universes, there's no boundary really, and you have to use some internal degrees of freedom as a reference. Then, so classical frame relations, or maybe let me abbreviate that a little bit. So classically, frame relations really encode space-time structure also. When you think about the Poincaré group, for instance, the Poincaré group encodes basically the entire information of Minkowski space. And the question is also when we have quantum reference frame transformations, does that tell us something about the quantum structure of space-time? That's a question at this point. So again, similarly to how Poincaré transformations encode information about the background geometry, or classical geometry, could we extend something like this as a new paradigm also for gravity? Then it turns out in quantum information protocols without external frame. So you can imagine you have Alice and Bob, and they sit in their labs, and they've never met before, but they would like to do a quantum communication protocol, perhaps even teleportation or something like this. The standard protocols, they always assume that Alice and Bob that they agree on a reference frame, so that when Alice tells Bob, do a measurement in X direction, that Bob knows what she means by the X direction. But it may be, of course, that Bob doesn't know what she means by the X direction, and then how can they actually communicate the quantum information? And this has led to a whole wave of developments of quantum reference frames about 20 years ago. And then sort of a recent interesting development was a realization by Chandrasekaran, Longo, Pennington, and Witten. They didn't call it quantum reference frames, so we showed that they are quantum reference frames. But it basically leads to the observation that quantum reference frames can intrinsically regularize entanglement entropies in I should say, in quantum gravity. It's important that it's gravity. So this is a topic that maybe tomorrow, hopefully we will get there. Okay, so these are some motivations. Of course, you could have others. Okay. So now, so we're going to come back to this question: how do you jump into quantum reference frame perspective, and how do you change it? And as often in physics, there is no unique answer to such a question. So it depends on the physical premises that you make, and yeah, the kinds of background assumptions that you have. So, so the question, I call it Q, has no unique answer. So this is maybe a little bit, at first, a little bit disconcerting for the novice in quantum reference frames, because the upshot of this is that there's many different approaches to quantum reference frames. And so which one is the right one for the type of question that you're interested in depends a bit on what you're interested in. So, so important really, there's many distinct approaches to QRF relativity. And I'm just going to throw you a few names out here. I'm not going to make the effort to explain them all. Some of so we're going to be discussing really one approach in this lecture series, the one that's really made for gauge theory and gravity. I mean, I guess we're in quantum gravity gatherings here. I will hopefully discuss some of the distinctions with respect to some of the other approaches as we go along. At the moment, you will not understand that, of course, unless you know this topic, but I just want to give you sort of a list of different names, because there's been a lot of confusion in the literature, and you need to be aware that there's actually different approaches. So there's a so-called perspectival one. It's one that only works with internal perspectives of quantum reference frames without any sort of global perspective. There's so-called algebraic ones. There are effective ones. They're based on effective techniques. There's a so-called quantum information approach. That's the one that's mostly has been used in these developments of quantum communication protocols. There is an extra particle one. There is an operational one. Wondering if I'm missing anything. And then there's the perspective neutral one, so that's the one we're going to be discussing. See if I missed anything. Maybe I've missed some, but it doesn't really matter. So the main thing is that in general, they're inequivalent. And so so the question comes, so which one should I use? So it's a little bit more subtle than this one. It's really also important that I say in general inequivalent. There are also equivalences between them for some cases. Okay? So for instance, so in fact these guys here, they're equivalent for so-called ideal quantum reference frames. I will explain what they are. Later today, ideal quantum reference frames are those that have sharp orientation states, so perfectly distinguishable ones. And the other ones are, there's some kind of connection here, but basically the rest is generally distinct. Okay, you can recover basically, in some sense, you can think of this here as a special case of the extrapolated. But anyway, it's hard for you to follow this without seeing the details. But it's just, you can see that there's a bit of a, when you're new to the field, a bit of a complicated situation. You have all these different approaches. In general, they're inequivalent. In some cases, they are. So what do I do? And yeah, that's a question.
I have a question. By quantum, do we mean that we are quantizing the space-time into discrete, or we are considering a continuous space-time in quantum systems?
Okay, yeah. So here at this point, I'm really being quite generic. So in fact, in the beginning of this course, when we discuss quantum reference frames, we don't even consider space-time. So later on, we're going to be discussing space-time. So you can think of quantum reference frames even in mechanical systems.
Okay.
So that's important to keep in mind. So there's, at this point, no space-time. So tomorrow, probably when I talk about this stuff here, these regularizations of entanglement entropies, there will be space-time, and then probably on the last day. Well, okay, negation theory also. But I have one being quantized. Okay, so...
can I ask a question?
Sure, yeah.
So I found your recent paper with the title Trinity. But is that circle road, is that related to...
No, that's something else.
That's something else. Okay.
So that is... so that one is purely perspective neutral. But that is actually one that showed that different approaches to relational dynamics are equivalent, actually. So there's this Page-Wouters formulation, relational observables, there's certainly parameterization, and Trinity is an equivalent of all of it. Basically, by that equivalence, they're all incorporated in the perspective neutral approach. And in fact, I will probably discuss this at a somewhat more general level today, hopefully.
Okay.
By equivalent or equivalent, what do you mean by that? Is there any physical observable you can compute? Or?
Yeah, by equivalent, literally that, physical observables. So at a general level, I should say expectation values, everything is the same. So in that sense, you can say they're just different representations of the same theory. And so I say expectation values and so on because when it comes to, so these two here for ideal frames, you can literally see that it's like literally the same. The perspectival Hilbert spaces, the quantum reference frame transformation are literally exactly the same. These two guys don't work with Hilbert spaces. This is an algebraic approach that uses an algebraic perspective on quantum theory, so algebraic states and so on. And this here uses a quantum phase-based description. So at the end of the day, these guys you can really only compare at the level of expectation values. And then, but then at the level of expectation values, they're the same.
And by equivalent, even at the level of the expectation, but values are different.
When I say inequivalent, yeah, that's right. Yeah. I mean, the thing is that here you can draw, so for ideal frames, so in general they're inequivalent, but for ideal frames there is an isomorphism between the sets of states. Okay, but for instance, these guys, these three, they consider state spaces that are much bigger than the other ones. So it also turns out that this one in general has state spaces that are bigger than this one here. So I think I need to go a little bit along for you guys to understand this a bit better. So here, we're going to go perspective neutral. And maybe let me just use the acronym PN so I don't have to always spell it out. Why it is called perspective neutral, this will become clearer as we go along. So this one is singled out by the following. So I'm just throwing that at you. We will see why later today. So it's the appropriate one for gauge theory and gravity. In fact, also for quantum error correction. It's something that I'm not sure I will have time to discuss in this lecture series. It's the most radical. And what I mean by that is it really leads to the smallest state and observable spaces. And the reason is that we're going to be treating any external information as gauge. So it's actually spelled out in the language of gauge theories. And anything that's external is going to be treated as gauge, and that way you end up on the smallest surviving set of states and observables in the end. So that's really the distinction of this approach compared to these other ones that don't treat external symmetries as gauge. It's only fully unitary. QRF transformations. In general, when I say in general, that means also when you have fuzzy frames and so on. So that's the only approach that can do this. And that's really because they're related to gauge transformations. So really here, so if you have the idea that your quantum reference frame, an analogy to external reference frames that you're used to, that it really serves the role of defining an internal description of the system, but really nothing more than that. And changing internal quantum reference frame should not delete any information. It's just a change of representation. So it should be unitary. That's the one that you should pursue. So okay, I don't know if you can read this, internal descriptions. And change basically without loss of information. Okay, I don't know if you can read this. This is maybe for some of you a little bit hard, but the precise wording may not so important. So without loss of information. So it's really, as we will see, you get something like quantum coordinate changes, and it's really like coordinate changes on the manifold. You're just changing the representation, but you don't lose any information. So that's one thing. So what else do I have here? Let's see if I forgot something. There's one thing. So I'm going to continue here. This is one thing that we'll discuss today. It's, it mimics the covariance structures of special relativity. It's also the only one that can do this. This is also how I will introduce that approach. And it's really, okay, you can, if you have heard about the relational paradigm, so this is something that, of course, has been going on in quantum gravity since at least the 60s, even going back to Wheeler, DeWitt, and so on. That in quantum gravity, you should invoke internal reference degrees of freedom. But surprisingly, over decades, actually, it was never really considered to do changes of these internal degrees of freedom, and that's really something that we've done in recent years. So you can view this really as a completion of this relational paradigm in physics that you have an internal notion of covariance in a sense. But one thing that maybe from this whole melange of approaches here is that overall you can view quantum reference frames in some sense as a universal tool for dealing with asymmetries in quantum theory. So I say that somewhat loosely because depending on the setup, we don't have quantum reference frames yet under full control. It's just like it's in some ways still a somewhat young field, but it's fairly clear that this should also extend to full quantum gauge theories and so on, and I will explain some of this hopefully tomorrow. And I say universal because really, you have these different approaches, and the conclusion is also there's not a single right one in general. These other approaches here, they still have merit. It's just that they have a different scope of the one that I'm going to describe. Okay, so this is kind of the basic background of quantum reference frames, and so now I will proceed to introducing this perspective-neutral approach. Or maybe first of all, I should say a few things of the scope of these lectures. We'll do PN approach versus special relativity. When I say special relativity, I really just mean a facet of it. So we'll do some details of this approach. So in the beginning, I will really kind of introduce some of the structures of this approach in parallel to special relativity with internal frames. But I will not yet explain some of the things in detail. I will do that afterwards, but I want to compare it first so you get an idea of what's going on, and then we go into some technical detail later. Then hopefully, it depends a little bit on how we progress. We'll discuss relational entanglement entropies and aspects of thermodynamics. Then we want to discuss relational entanglement entropies in perturbative gravity. So this relates to this work by Höhn and so on from a few years ago. Then QRFs in gauge theories. So this will also include the discussion of edge modes. So you might have heard about edge modes. You can interpret them as quantum reference frames. I hope I will manage to discuss relational entanglement entropies in lattice gauge theories. So this is where quantum reference frames lead to a really new perspective. That's encompasses really everything that has been done on this basically before. It's that in a new light. And then I would like to do. Let me just write for the moment internal frames in gravity. Hopefully also in quantum gravity at some level. And then this last part, maybe there's no time for this. So we recently showed that there's a correspondence, really a dictionary between quantum error-correcting codes, group-based codes, and quantum reference frame setups according to the perspective-neutral approach. It's really a dictionary. This is also a nice way of thinking about gauge theories and so on and so on. Okay, so this is roughly the plan. But whether I manage to cover all of this depends a little bit on how we progress. Okay. So what's the time? We started at 10:30, right? So we're good. Okay, so yeah, we're already behind schedule. So are there any questions at this point? Okay. So this is going to get more technical eventually. Okay, so it's so we're going to do now the PN framework, if you want, the perspective neutral framework. And as a first step, we now need to discuss the distinction of external versus internal frames. This discussion here is not dependent on quantum theory. So we're going to be given some group G. And yeah, we're interested in frames associated with it. So the reference frames are, of course, always associated with some kind of symmetry group. Now, like, you know, Lorentz frames with a Lorentz group and so on and so on. But really the important thing is, and I mean that maybe has already come through a little bit when I say we're going to look at square reference frames in gauge theories and also in gravity. This G doesn't have to have a spatial temporal interpretation, so it doesn't have to be like the Lorentz group or something. So let me just. So it's really. So we're really looking at a much more general notion of frame, so really a somewhat more abstract notion of reference frame. And one of the premises that we want to make is, so we're given some system, also given a composite system. It's called S tilde for the moment. I'll put a tilde here because later I'm going to be using an S without tilde, but it will be a subsystem of this. And we'll have that states rho and some G dot rho. I'm not precise about what the group action is at the moment. It could be, rho could be quantum state, could be classical state, and I have some group action on it. And the premise is that these states, that they're going to be indistinguishable without an external reference. So the way you can think about this is, so somewhat pictorially, I mean, it's like you have a bunch of subsystems, and there is some group action on it that transforms this. The statement is somehow that you can't distinguish before and after if you have no external reference. But of course, in order to distinguish at some level, rho and G rho, I must have, you know, well, it must be distinguishable relative to something, and that's something we're just going to identify as an external reference frame for the group G. So, so we have an external frame for G, and relative to that external frame, you can distinguish the states rho and G rho. Okay, so that's the basic idea. Now, for instance, this external frame in quantum information or also in quantum foundations could be it could be a lab frame, so outside of the quantum system of interest. So it could be a physical reference frame, literally. But you know, typically in gauge theory and gravity, it's fictitious. Yeah. That reference frame. So there's no physical external reference structure. So you can think of this. So and this also goes in line, of course, with in gauge theory and gravity. This G will be, for instance, whatever the gauge group is. So in gravity, for instance, it will be the small diffeomorphism group. So about diffeomorphisms. And so the question here is then, so what's distinguishable without the external frame? And so here, what we're going to do is, so this is basically the premise again of the PN framework, is we're going to do the most radical thing that we can do in identifying any external frame information as gauge. Okay. So G as basically external frame transformations. And so we're going to call this gauge transformations. So we're going to treat it as gauge. I'm going to put here quotation marks for the moment because, again, if you do this in quantum information foundations, it's not literally a gauge group, but you're going to treat it like a gauge group. So our idea is really to wipe out any external information by treating it as gauge. And in particular, if we now talk about external frame independence, another way of saying this is just gauge invariance. Okay. So you can think about gauge invariance also in general relativity or in gauge theories really as an external frame independence. But it's an independence of an external reference frame associated with whatever the gauge group is. So for instance, in general relativity, this would be some arbitrary set of external coordinate systems, so unphysical coordinate systems. Okay? Or in gauge theories, a fictitious frame that can distinguish non-invariant states, for instance. Okay? Maybe say gravity G is going to be typically small. Diffeos, or you could also say general coordinate transformations. Just with a bit of intuition. Okay, and now we want to ask what is distinguishable without access or recourse to this external frame. Well, we have some composite system, so we want to pick out somehow a subsystem. So we want to pick out subsystem, let's call it R, of maybe let's write S tilde as RS. So we have some frame subsystem and a complement of it, where you can think of this being defined relative to the external frame. And we want to basically use some internal degrees of freedom to describe the rest. So if you have a bunch of particles, you could think of using some particles as a reference to resolve rotations or defining relative distances or something like this. So really, you can view a quantum reference frame as a choice of split between redundant and non-redundant data. So really the QRF is the redundant part. You don't want to describe the reference frame relative to itself. It's a bit tautological. So the quantum reference frame is to absorb the redundancy. Now, of course, in order for this to be feasible, the reference frame has to be as non-invariant, loosely speaking, as possible. So, really R as possible. So I will, this will become, I will be a bit more precise, so what I mean by that. But it's clear that if you have something that doesn't change under the transformations in the bad reference frame, it's like a clock that doesn't evolve, it's a bad thing to retime, right? So in some sense, you want to have something that is as non-invariant as possible. And then, then as I said, we want to describe the rest relative to this. So this is basically the conceptual underpinning of the story. And now let me introduce the perspective neutral approach in parallel to some structures of special relativity with internal frames with tetrads. So this, if you have any questions on the conceptual part, this is a good moment to ask. Yeah.
So in your framework, the subsystem R is viewed as an external frame.
No, sorry. R is an internal frame. So quantum reference frames are always internal. So I mean, it's internal to S tilde, right? So this thing here, sorry, maybe I should have said this. So this, so this here is S tilde, the whole thing. So the whole set of balls, for instance, that's your S tilde, and then you could pick out, let's say, this guy here. Maybe that's your reference frame or something like this, some subsystem of the total thing. So I mean, if you have the Euclidean group, for instance, that you want to, so maybe as an example, if I just have G, the translations, and I have a bunch of particles on a real line, one particle is enough to serve as a reference frame because I can just define relative distances relative to that particle. So if I have n particles, I can just pick any one of these particles as a reference frame. You could also choose something more complicated, center of mass or whatever, but any of those would be a valid choice. If I go to the Euclidean group, then I have rotations. So I can still define relative distances to one of the particles to get rid of to deparameterize the translation part of it. But in order to take care of rotations, I have to define directions, so I actually need more than one particle. So in fact, I will need 3 in that case.
Yeah, I was curious, like why we are not part of the system?
Well, that's
we are observers.
Yeah, so that's a good another good philosophical question. If you have maybe you've noticed that I never really talk about observers here, because I'm distinguishing reference frames from observers viewed as agents. Okay? So really, this is only about reference frames that in principle serve as a platform for defining a description of a system. Whether or not the observer is part of the system or not is a separate question. Of course, when you are talk about quantum information or quantum foundation setup, and clearly the observer is external to the system. It doesn't make sense to think of the observer as sitting in the quantum system that you're investigating. But it may be of interest in some cases to not use an external reference frame to describe that system. This is, for instance, when there's Alice and Bob and they want to describe something without actually sharing an external reference frame. But if you're in, for instance, quantum gravity, okay, that's a separate question then. If you have a closed universe description, at some level you want to internalize the observer also. But in which case, yeah, they would be part of the system. But the thing is, this goes into quite philosophical questions. This whole framework is agnostic to that, how you interpret the observers. Okay? So there's no need to talk about observers per se. It's really just a story about reference frames.
Is a single reference system sufficient to describe all the dynamics of the system?
Well, in general, no. So I mean, here I'm being quite simplistic. Of course, when you have, for instance, in gravitational systems, we will see that the reference frames are actually field-dependent coordinate systems, so they depend on the field content. And just like coordinate systems in general are not covering all of space-time, the same will be true for these dynamical frames in gravity. They will only be, like coordinate systems, only valid in a patch of space-time. And so then if you want to describe everything, you need many of them.
So like the redundancy you mean there is something like even if you use multiple patches to describe that, there is some overlap and
yeah.
Overlap.
Okay, so I mean, so this is maybe a little bit down the road, but the thing is that, for instance, it is sufficient to use a single reference frame for a patch of space-time, for a patch in field space, because it also depends on the field configuration, how, for what field configuration the frame is valid. So you can think of, for instance, in gravity, you can shoot in geodesics from the boundary, if there's a boundary, and then use the geodesics, the endpoints of it, to basically anchor bound points to the boundary. But when you define a geodesic congruence, at some point they may be caustics. Where the caustics are depends on the field configuration, right? But for the region in field space where there are no caustics, that geodesically defined frame is a good reference frame, and it absorbs the entire redundancy for that part of space-time. Okay? So whenever I use such a reference frame, it still has, ultimately it should eat up the entire redundancy for whatever I'm interested in at that moment. It may be incomplete in a full space-time sense, but not in the redundancy sense. Okay, any other question? Okay. So yeah, I don't know, I guess I already said it, but so yeah, R is internal, of course. That's the whole point of it. And of course, one other question is then, in general, there's many different subsystems that I could pick as an R. Okay, so I mean, just you know, for instance, inside S, it may be a very complicated system. There could be many other choices of reference frame. Then the question is, how do I jump into a frame perspective and how do I change it? Okay, if there are no more questions, then let me start discussing now the.
Excuse me.
Yeah.
So in this framework, and implicitly, and we assume there exists more than 1 degree of freedom.
Yeah, I mean there have to be sufficiently many degrees of freedom, of course, for this to be interesting. But it's basically as long as you have a theory that supposes it's a gauge system, as long as you have non-trivial gauge invariant data, you will have it.
Yeah, I see.
I mean, of course, you can have a single particle on a line subject to translation invariance. There's nothing there.
Okay.
I mean, it's a trivial theory. So I could use that particle as a reference frame, but I have nothing else to describe. So it's. Okay. Okay, so this will be hopefully a little bit less wordy, a bit more technical, but I think it's because it's a little bit different. The ideas underlying this than what you may be used to. I think it's important to highlight some of the conceptual underpinnings. Okay, so now we want to do basically SR versus QRF covariance.
Actually, I have one question regarding previous question. So, like, when you say S tier that use RS, do you mean the factorizing Hilbert space, or like, because even if for the single systems, let's say we have 2 commuting or something.
Yeah, in general, no. So I'm being here. I mean, in this conceptual part, I'm being quite a bit hand wavy, of course, because it's a general sort of conceptual message that I'm trying to convey. What it may mean in practice depends a little bit. Of course, in some cases, I can say that this will be a tensor product structure, but in general, no. So, for instance, on lattice gauge theories, I can have something like this, but if I'm in a continuum gauge theory, I will not be able to write the total kinematical content of my theory as reference frame tensor rest. This will just not work in general, and in gravity, much less. But so whatever that split there is, I haven't been precise here because it means different things in different contexts. So I guess I should say the PN way. So we're going to do. I'll take a little bit of space now. So we're going to do special relativity with internal frames. And then let's do QRFs here. So my aim is to compare them, basically. Okay, this was already a bad start. I should do it like this. So what we're going to be doing is, okay, maybe I should have explained that separately. But so you can think, for instance, pictorially. Here I should say for some unimodular group. G. So unimodular Lie group, really, I should say. I mean, you could generalize this beyond unimodular Lie groups. It just turns out to be very convenient to do this. Unimodular means that the H measure is both left and right invariant. Okay. And a very simple example. So I should say, okay, unimodular groups. Okay, they're finite dimensional Lie groups. So what we're going to be discussing now is not field theory. It'll be mechanical quantum reference frames. Field theoretic quantum reference frames we'll do later. And unimodular Lie groups really encompass most of the symmetry groups in physics. Any abelian group, any compact Lie group is unimodular. Poincare group is unimodular, and so on, and usually also all the structure groups and engaged theories are also unimodular groups. Okay. So it's not a very restrictive. Physically, it's not very restrictive. Mathematically, of course, it is. So, and we can think of. I'm just going to draw this here. We could think of, for the moment, we have some reference frame R, and maybe some system. Call it S, and it's really, in the simplest case, it could be G, the translation group, and they're somehow on a real line, and G, the translation group, acts on it. So in the picture, I'm going to be using this, but the formula is in this spell for any unimodular group. And here in special relativity, really what I mean by this is we're going to be looking at we take some Lorentz frame. We consider it as the external reference frame. So I'm going to be writing external. Okay, this is going to be very hard for me to read. Okay, sorry, this is becoming a little bit messy here. So we're going to take this as an external Lorentz frame. And then our internal reference frame will be some tetrad. So E0, E1 say. And our system, for simplicity, is going to be, we use what's blue over there, so I'll use blue here. So let's write it like this, so it's some form of velocity. Could be some tensor, it doesn't really matter. So this is our system, and this is our tetrad. So this is our internal frame here. Okay, so this is the internal Lorentz frame, and this here is a system. And so what we want to be doing now, so we're going to be treating, so what I should say is when I write here also mu, the space-time index, that's with respect to the external frame. And we're going to be having internal frame indices that are, they correspond to the internal description. So here, when I say special relativity with internal frames, so I mean special relativity with tetrads. In principle, of course, to deparametrize the whole Poincare group, I would also have to look at the position part. You could easily extend this, but I'm going to ignore the position part. So I'm only going to look at the Lorentz group. So now, the reason I will explain this in comparison is that you will see really that this quantum reference frame setup will mimic at a somewhat abstract level exactly what happens at the special relativity level. And so then it will be much less surprising to you why these things happen on the quantum reference frame side. If I didn't explain that in relation to special relativity, it would be harder to understand. Okay. So first thing is, the internal frame. Configurations. So what are they? So here it's a tetrad. So we write it as EUA. And this here is the space-time index. That's the frame index. They both will play an important role. So And now the thing is, a crucial observation is that E mu A, that this is Lorentz group values. Okay? So I'm going to choose SO plus 31. You don't have to. You could just take any. I mean, it's basically choosing the handedness orientation of it. You don't have to, but for simplicity, I'm going to do this. So this, of course, follows by So this follows, of course, from the fact that from the normalization from this here, I can read out that this is Lorentz group values. Okay? So that's one really important observation, that reference frames, the configurations of the reference frames take value in the group with which they're associated. So we have group values, frame orientations. Okay, one thing, so here, at first I say internal frame configurations, and really, I'm going to put a quotation, we're going to be defining them as the frame orientations. Right, so here this is clear. If I, in this tetrad example, you pick a particular configuration, of course, some specific group element for this that tells you how in this external Lorentz frame the tetrad is oriented. Right? So in that sense, it makes sense to call this a frame orientation. And now we want to do the same thing on the quantum reference frame side. So some Hilbert space. HR. And then, okay, one thing that I forgot here to say, and it doesn't fit. Okay, no, maybe I'll do that as the next point. But yeah, let me maybe introduce the next point and we go a little bit clearer. So, on the quantum side. Actually, let me maybe see if I can squeeze this in. So, the important thing is, of course, that these frame orientations, they transform covariantly under gauge transformations. So, oh, yeah. No, maybe let me just do this again over here. So here, going to be SR and quantum reference frames. So what are the gauge transformations? So again, when I put gauge transformations in quotation marks, it's because it's really external frame transformations. So it'll be lambda nu, and again SO31. So it's the one that acts on space-time indices. So it'll act on this guy here. And the important thing is that because, of course, you have space-time indices, it'll act on every system in the game, so including also on S. And so we have lambda nu. I guess I should have repeated here. Sorry. The indices don't match the. Way I wrote it. So you have this, and you also have. Nu, so acts on all systems, all subsystems really. And so here for the Hilbert, on the quantum side, we want to mimic this now. So so we have some Hilbert space for the reference frame, and what we want to do is want to pick a so-called covariant POVM. Because what I need is an observable that describes the configurations of the frame, and I want to have, of course, a probabilistic interpretation over the orientations of the reference frame.
Yeah, maybe you have to explain, but I'm confused that why do you follow the gauge transformation? It looks like a usual global sequence.
Well, that's why I'm putting it in quotation marks here.
Yeah.
So really, it's an external reference frame transformation. So
yeah.
here, so so the aim here is we pick some external reference frame, we throw in a tetrad, and what we want to do is we want to describe everything relative to that tetrad. So in this case, okay, that's just one pore velocity.
You don't restrict yourself to the observable which is invariant under this?
Yeah, we will do. Yes.
Oh, then I'm confused because if it is global symmetry, we can talk about the quantity which is covariant under transformation.
Yeah, that's right. If you so here I'm interpreting these external Lorentz frame transformations really as gauge, so as external reference frame transformation. I want to go to an internal description that's completely independent of that. So it's a bit like in a laboratory, if you have an external frame that may be physically relevant, but I want to go to purely internal description. So what you will see is that this internal description is essentially like standard relativity. It will mimic exactly that. Okay. So, but it turns out that this is a very convenient way of introducing these internal descriptions. Now you can, of course, also ask, why would I want to do this? Why would I want to go to an internal description? I mean, first of all, okay, thinking about literally arguably it's a more physical thing to do. That I think about degrees of freedom like a tetrad, and I want to describe things relative to that. But you can think of this also from the point of view of gravity in the end. That in gravity, we want to describe everything just in a purely internal way. Of course, here in standard special relativity, you don't really have to do this. But you can use it as a step in that direction. I mean, so special relativity has a special case of general relativity in that sense. Yeah, but this is the reason why here I put quotation marks, because they're not literally gauge transformations. So they're really, they're external frame transformations here. So that's why I made that distinction before also. But on the point is that you can treat all of this in the same way, and the formalism is kind of agnostic to the precise interpretation of this. And in particular, this quantum reference frame setup, it works also literally for gauge theories. So anyway, so what we want to do now is we want to have a configuration or an orientation observable for the reference frame. And what we want to have is basically I'm going to be a little bit abstract now, and then I'll give you some examples why. So, so covariant POVM is a set of effect operators that define your probabilities. Or who's not familiar with POVMs here? Positive operator valued measures. Okay. All right. So let me say a few words about this then. Let me maybe first of all spell this out. And then I'll explain a little bit more. Okay, one thing that I forgot to say is there's here for simplicity, we assume there's a unitary representation UR of G on that Hilbert space. That's going to be necessary. You could also use projective representations, makes it a little bit more complicated. But what you want is essentially that these effect operators, that they transform in a covariant fashion, which I will take to mean this here. So remember, and X is some Borel set over the group. So it's a measurable set over the group G. So what are we seeking here is, again, it's something, as I mentioned here, the orientations of the frame take value in the group. So that's why I want to look at a probability measure over the group. The group we will take as the configuration space of the quantum reference frame. And so I'll give some examples that will make this a little bit clearer, but I guess since people are not familiar with positive operator valued measures, maybe as an interlude. So so this is a POVMs. So this is a standard tool in quantum metrology and really also in quantum information, I should say. So they are, in some sense, the most general types of measurements that you can have in quantum theory. And really, I mean, you may be familiar, of course, with a spectral decomposition. So you have some observable O, and then you can write it as OA, and you have some, you have a spectral decomposition. If it's a Hermitian operator, then you can take these guys here. Let's call them EA. They're of course projectors in that case, right? So I will have that EA squared is equal to EA, so it's a projector. And of course, assuming that this observable is really that is non-degenerate, and this is a full basis on the Hilbert space, I'll have a resolution of the identity. So meaning I have something like this. Okay. This is if it's non-degenerate. Okay. Of course, not in general. For simplicity, let's assume this. And of course, one other thing is that I have that EA dagger is equal to EA. And so it's clear that this defines us a probability measure, right? So these EAs, I can take them as a probability measure because I can now have some state phi. So and this is going to be the probability A that the outcome, if I do a measurement of the observable O in some quantum state quantum state phi, that the outcome is it's this. No? So in that sense, and you can see this also because the these guys here, they're so-called, they're non-negative operators. Non-negative means that that this here is always going to be greater or equal to 0. Of course, in fact, if you normalize this appropriately, then you'll also have that, it'll be like this, right? So in that sense, these objects here, they define you a probability measure over the outcomes of that observable O. And so this is a special case of a positive operator valued measure. So it's a positive operator, which means this here. It's a probability measure because it gives you a resolution of the identity. I can add the different outcomes up together, and I get the full thing. So this here tells you basically, this normalization tells you it's a probability measure. But it's a special case because the elements of that POVM are projectors, and they satisfy this condition here. So this is a special POVM. It's actually it's a so-called PVM, which is a projection valued measure. So this is the standard case that's if you don't work much in quantum information or so, that people usually consider. But the main point is that you can have something more general than this. Okay. So I can have, okay, where do I continue writing? Because I don't want to wipe that out. Can I wipe this out here, or it's an interlude? It wasn't planned to be part of the talk. So now the thing is that a positive operator valued measure is in general, you have some configuration space. So in our case, G is the configuration space. And what you want is that you have an E of x, so where x is some measurable set over the group. So it's a generalized. So in the previous case, I had discrete outcomes. If the group is discrete, well, this will also just be elements of the finite group. But in general, if I have a continuous group, then I have to take, the next step is basically measurable subsets. And the idea is that we define effect operators that are also that are non-negative, semi-definite operators. So what we want is also that they satisfy this here, okay? And then that if they're additive, if I take an I and I look at xi, that this is E of the union I xi provided xi prime is the empty set. So if the intersection of them is 0, then they're additive. So in this sense, I can, it is the kind of continuum version of when I had these EAs. I can start summing them over some range of A's, okay? And they're of course all distinct in that case. This here is kind of the analog of this. And what I also want to have is that if I, here in our case, if I take E of G, so G is the maximal Borel subset, so it's the full group. I want that this is also normalized. So this is the definition of a POVM. But note that in general, so also, okay, what I should say is also that E dagger is E, so they are Hermitian operators. That is also true, but in general, we will not have that E squared equals E. Okay, so this will not be true in general. So what does that correspond to? It means that the probability measure that you have is not that different outcomes are not perfectly distinguishable. Okay. So here in this case, I had a discrete set, and different outcomes A are perfectly distinguishable because here we had, what I forgot to say is if I have EA and EB, this is 0 for A not equals to B, right? Because they're actually orthonormal, these projectors. So, and here in general, I don't necessarily have to have that, if I take EX, EY, they don't necessarily have to be 0 for XY intersecting trivially. Okay, so this means it's a generalization of a probability measure where the outcomes of random variables where they're not perfectly distinguishable. So it's really a fuzzy probability measure.
Excuse me.
Yeah.
Can you somehow motivate why we have to generalize this properties?
You mean why to go to these POVMs?
Yeah.
Yeah, this gives you much more power. So the thing is that generic measurement or probability measure in quantum theory is of that form. If you restrict yourself to PDMs, so these idealized projection value measures, for instance, with quantum reference frames, that's a very special kind of quantum reference frame, and generically it will not exist.
I see.
So, for instance, in gravitational series, it will actually I will probably illustrate the difference. So maybe I'll do that. Okay, I guess time is running short. But it's the ultimate reason why we want to go this way is really that it allows us to cover significantly more stuff. Okay. So now this here is basically the definition of a positive operator valued measure over a group G, but covariance is something else. So the covariance is an additional property, and covariance is this here. That I want to say that these, the group here acts on itself. Okay? I want that these, sorry, what I should say is that these guys here, they're so-called effect operators. And these effect operators, they should transform covariantly under these G transformations. So I'm assuming I have a unitary transformation on that frame Hilbert space. And what I want is that these effect operators, that they transform covariantly in this sense, that they just translate by G the Borel set over which I'm integrating. So this is maybe a little bit abstract, so let me go into illustrating this. Okay, can you give me 5 more minutes? I'll try to, so in nice examples you will see, right? So indeed, so one way to realize this is to choose a generalized coherent state system. So what I mean by that is, so we have a phi of G, R, and then R of G, and then G and G. So a coherent state system, really, that means, actually I should probably write that here. Yeah, well, let me write here. So what we mean by this here is basically you take phi of G, R, and you write it as UR of G times some seed state. So E is the identity element of the group. Okay, is that clear? So I say generalized coherent state system. So this here clearly is a covariance condition, right? So I have I pick some seed state, and when I say generalized, we'll be allowing that there are also distributions. They don't have to be Hilbert space elements, okay? So there can be, for instance, when we think about reference frame for the translation group, we pick a particle, there can be position eigenstates. And the idea is that you get an orbit of states. It could be within the Hilbert space, it could be in the sense of distributions that has this covariance property. So why am I doing this? So I'm going to be calling these coherent states the orientation states of the system. So the orientation states, now you will see they're also labeled by group elements. So in this sense, really the configuration of the group, the configuration of the orientations of the frame are group valued, just like the tetra takes value of the Lorentz group here. Okay? And they transform nicely in a covariant way under these transformations, and you should view this here really as the analog of this relation here. So the tetrad also transforms covariantly. Here, the tetrad transformed, I mean, this is an action of the Lorentz group on itself, right? So this is a representation of the Lorentz group. This here is at least Lorentz group valued. And this here is kind of the analog of this. So you have the representation of the group G, and it acts on itself in the sense of coherent states. And now, so this is not the only way in which you can define covariant POVMs, but it's a very convenient way. In fact, I realized that I should probably say something more here that doesn't quite fit there anymore. So what I'm going to write here is still to be part of this down here. It's not the counterpart to this part. Okay, I'm sorry. So let me. So this is a bit separate. So now we can define effect densities. by just setting, by just doing something like this. Oops. Phi of G. So I'm just taking a ket bra of these generalized coherent states, and we can consider this basically as this is a density, and then the effect operators, I can just define, sorry, this is the H measure here, the dg. I can just define this as this, where I'm integrating over the monad set x. So really this is nothing else than x dg, and then I have this phi of g, phi of g. And now the statement is that these are going to be positive operators. So I mean, this is, since time's running out, I'm not going to explain this in detail, but it's basically if you take expectation values in a given state, you know, we're going to be sandwiching this here with a bra phi and a ket phi, and then you can, is that clear? So basically I have phi of g, phi of g, phi, and so this is just phi of g. So it's because of this really. No. So it's a positive semi-definite operator, and the requirement is that they give you a resolution of the identity. So meaning, if I take E of G, so I just integrate this whole thing up, and I get the identity of the reference frame Hilbert space. So this means that that this generalized coherent state system, that it provides you a basis. Maybe an over-complete basis, but it provides you a basis for this Hilbert space HR. Okay, and now the thing is that this is covariant, is guaranteed. This is because I can, okay, actually, so proving it is pretty quick, but I'm wondering if I skip this part, and I let you do this as an exercise, because time is running out. So covariance is guaranteed, so it's basically, you know, it is guaranteed from this property here. Yeah, so because the coherent state systems transform covariantly, this means that these guys transform covariantly, right? So I can conjugate this whole thing by UG dagger, and then by this covariance property here, all that will do is it will change the argument here. Then I have the invariance of the H measure, and then I can do some manipulations to show that it is actually satisfied. Okay, so coherent states give you covariant POVMs. But you know, proving this is okay, 3-4 lines, but you know, I guess it's lunch, so I'm not going to do this. So exercise. Okay, I was going to give you an example with a translation group. We're already over time. Maybe I do this after the lunch break then. What do you think? I mean, sure. Would it help now? I mean, it would probably take another 5 minutes or so, but we can also do it after lunch. So that then this would be a concrete example that's not, because this is kind of abstract right now. So I think it's up to you guys whether I do it now or after lunch.
Maybe after lunch.
After lunch, okay. So it will become a bit less abstract then. Okay. So yeah, so what we have done here is really we're setting up at for the moment really for some general unimodular group, the notion of frame observables and a probability measure over the group itself, and that's the ultimate definition of your frame observables. And the frame orientation states are these guys here. Okay, so I guess that's what I forgot to say. These are the QRF orientation states. Okay. Any questions on this so far? I hope this will become a little bit when I illustrate this in a concrete example after lunch break, I hope this will become a bit clearer if you haven't seen this stuff before. Yeah.
I think it depends on where to start with, but like basically, if you consider Rn like a composite system S to the Rns,
Yeah.
and if you single out some R, then like is there always guarantee that we can find this kind of covariant PLVM or this kind of generalized popularized state system?
So you mean on some Hilbert space HR?
Yeah. Because like typically there is an interaction between R and S, and this may not be acting.
Oh yeah. Right. So we haven't gotten there yet. So I mean, there's a few separate things we have to separate. I mean, in general, I will assume there is a representation on this unitary representation of G on this Hilbert space, or it could also be projective. That's an assumption here. If you don't have that, so it's true, I could in principle have at the end of the day, I haven't spoken about the system yet. I could have a representation on RS that's not a product representation, and I don't have an individual representation necessarily on the Hilbert space, then it may be a little bit complicated. So here I'm assuming that you can do this. In the case that you're referring to, indeed, I don't have a general answer to that because the completely general case, we don't know how to treat it yet, but the basic idea would be that you may have to pick a reference frame that's not pure R-based, but something that is a bit non-local in the RS sense, okay? But there are also cases when you can still do this. So for instance, if you think about Hamiltonian constraints in simple systems, you can have a Hamiltonian for, say, the clock, Hamiltonian plus a Hamiltonian for the system plus an interaction. Then, of course, you have then you have a possibility. So the Hamiltonian purely on the clock, that still defines your unitary representation on the clock Hilbert space, on the frame Hilbert space that you can use to build a covariant PVM in the sense. What is true is that, of course, that representation, when I use it on the full Hilbert space, is not the same as the representation that's generated by the full constraint. And then the question is, how do they match up? But in principle, I could still do that in that case, even though there's an interaction.
So, any questions?
Yeah.
So the frame orientation here, the meaning of orientation means the sign of the determinant of the Lorentz transformation.
No, I mean here I've just picked SO plus 31. So for the orientation of the tetrad, future pointing, and then I don't know, left-handed or right-handed, depending on what you want. And I'm for the moment only considering those, but in principle, there's nothing stopping you from going to the full Lorentz group if you want. So, but the orientation states, they are the configurations of the tetrad, right? So when I write the tetrad E mu A, I'm going to express it with respect to the external Lorentz frame, and of course, I can rotate that frame. I mean, we will see that actually after the lunch break. I mean, there's also, of course, a Lorentz transformation that acts on this guy here, right? So, and what will this do is it will reorient the frame. It will change. It will keep S invariant because it only acts on the A index, and S has no A index. So it will change the relation between S and this frame, the tetrad. So the tetrad in this picture, the background frame is invariant, S is invariant, and maybe. If it's in X direction, the boost that I'm doing, then I'll change the orientation of the tetrad, which means that after that transformation, before the transformation, this is a specific Lorentz group, corresponds to a specific Lorentz group element, and after the transformation is a different Lorentz group element. So in that sense, I have an orientation before I made the transformation and an orientation after, and they're not the same. But it's really the orientation correspond to all these different Lorentz group elements that I can cover by these frame transformations that act on A.
I see. So the orientation here means the orientation of the S mu.
Yeah, I mean the orientation is really which element of the Lorentz group does this correspond to. So I mean it's like when I'm here in the case where I have particles on the line, what's the orientation? It's the position of the particle on the real line. So and the position can be, any value in Q, but the position of the particle, any value in R on the real line, but the real line is the translation group. So the position of the particle takes value in the translation group. So that's another example where you can see that the orientations of the frame are group valued. And so yeah, the orientation is the position on the real line. It takes value in the group, and here it's really which SO31, which element of the Lorentz group does this one correspond to? That's the specific orientation of that tensor. And I can change it.
Any more questions? Okay, I guess not. Then let's thank Philipp for